So yeah, when I was invited to come here and be part of this, I waffled for an embarrassingly long time, sorry about that, because I wasn't sure I was going to have a lot to contribute. In fact, my research doesn't involve complexity at all, and it doesn't really even involve earthquake prediction. I got into that basically as a science writer, which is something I do in my spare time for the fun of it. I was interested in coming here for two reasons. One was for the opportunity to learn, which is not necessarily a good argument for me taking up space in the program. But also, when I started poking around online to see what complexity theory was about, I quickly found things like this that, I don't know if you can read it, but it suggests that maybe emerging theories in complexity theory might offer new insights into an old problem, namely earthquake prediction. And I should say from the outset that things are about to get a lot more concrete than they were in the initial talks. So if complexity theory could lead to new insights into earthquake prediction, it would be a tremendously exciting and valuable contribution. But for science in general and earthquake prediction specifically, an old saying comes to mind about remembering the mistakes of the past. Now, sitting and listening to the first two talks, it occurs to me that maybe for this audience, I'm setting up a silly straw man that I'm going to knock down. Maybe an understanding of complexity leads to an understanding that earthquakes are not predictable. But if I frame the talk wrong, I do have the advantage that we're sitting here about 4 miles from the peninsula segment of the San Andreas fault, which is that way. So you should be interested in what I'm talking about, whether or not it has anything to do with complexity. Okay, so let me move on to a couple of other quotes, which interestingly you sort of heard already. The first by Stephen Hawking about the nature of science. It involves the discovery of laws that allows us to predict events. And then maybe Ernest Rutherford, who I'm thinking maybe was the original materialist, saying all science is either physics or stamp collecting. Well, these quotes lead to something of an existential crisis for seismologists. As shown here, we spend our lives studying phenomena that have proven to be unpredictable. So, okay, what I'm going to do with my 20 minutes is start with some very simple earthquake prediction ABCs, and you'll see they're very simple, and then do a retrospective talk of the road that leads from the very basics and some of the basic ideas in the field that lead us to where we are today and in our thinking about earthquake prediction. That's cute. Okay, so to be useful, an earthquake prediction has to specify usefully narrow windows in magnitude, location, and time. And it has to be more accurate than a prediction based on educated guessing. And you can sort of illustrate that with what I think are pretty obviously useless predictions as follows. There'll be an earthquake in California tomorrow of any magnitude, and so forth. You can make a lot of predictions that aren't useful because basically they're shooting fish in a barrel. We know they're going to come true just based on what we know about earthquake rates. Okay, but as further illustration, I can put up a couple of predictions that maybe aren't quite so obviously useless. If I say there'll be a magnitude 6 or greater earthquake in California during the next 6 months, is that useful or not? There'll be a 7 or greater earthquake in California during the next month. That sounds quite specific, and that sounds like it might be a useful prediction. Okay, well, so earthquake prediction has proven to be a difficult problem. And again, maybe I'm setting up a silly straw man here. But for a couple of basic reasons. One is that the null hypothesis can be extremely tricky, and truly prospective testing, meaning proposing a prediction method that you're really going to test running forward, not looking at earthquakes that have already happened, is typically going to be done on geologic timescales and which is extremely difficult to do in a human lifetime. So, whoops. Okay, yeah, going back to these predictions, the problem with the first one is figuring out how likely that earthquake is going to happen just by random chance, and it turns out that that's not actually an easy question to answer. The second one, the problem is that it's a fairly specific prediction. It's unlikely to come true by random chance, but if you make that prediction and you get a hit, that doesn't prove your prediction method. You would need to have a track record of successful predictions to prove a method. Okay, so the difficulty of, I almost said complexity of, but the difficulty of earthquake prediction is sort of surprising when you think back to the basic tenets of seismology theory, which sort of suggests that we might be dealing with a predictable system. Going back 100 years, a little bit more, the 1906 earthquake, which broke the fault right behind us, led to one of the basic tenets in seismology, with what we call elastic rebound theory, and that's illustrated as shown as follows. So you have the San Andreas fault running vertically. You put a fence across the fault at the start of the earthquake cycle, the fault moves, stress and strain build up along the fault, and then the earthquake happens, and the stress is released. Now that theory lends itself to some very simple models of time and or slip predictability of earthquakes as shown here. So the simplest one is the characteristic earthquake model. You have a fault, stress builds up, it hits a failure threshold, the stress is released in the same size earthquake. And so it's predictable both in time and in the slip or the size of the earthquake that you're going to get. And in fact, we have some observations now that support the idea that there may be an earthquake cycle with a fair amount of regularity. One of the better data sets comes from across the bay, the Hayward fault. So this is looking at successive earthquakes just numbered through time leading up to the present. So these are large earthquakes on the Hayward fault. And in fact, it does look like there's a fair amount of regularity and predictability in that time series. The mean recurrence interval is 151 years plus or minus 23. The last one was 149 years ago. So you may have heard about this if you live in this area. So elastic rebound theory, almost as soon as it was developed, it lent itself to earthquake prediction, this idea that stress builds up, and if we can keep our eye on the system, we can know when an earthquake is likely to happen. One of the earliest predictions that bubbled up from the scientific community was made by this gentleman, Bailey Willis, who was an accomplished geologist from Stanford University, who in the 1920s was aware of some early results that led him to suggest or say that a large earthquake larger than 1906 was very likely within a span of 3 to 10 years. The media got hold of that and took the almost prediction and turned it into a full-fledged prediction, saying that Willis was essentially predicting that this earthquake was going to happen. So this was based on essentially elastic rebound and a result that came from early leveling data that purportedly showed that a full 8 meters of strain had built up along the San Andreas in just 30 years. So if you think back to that fence, if the two sides had moved 30 meters past each other, or 8 meters past each other in 30 years, that would be a lot of strain, and that's what Willis took to suggest that an earthquake was imminent. Well, so in fact, when that data were reanalyzed, the 8 meters of strain kind of evaporated. The actual strain accumulation was much lower. The prediction was debunked in spectacular fashion, and Los Angeles was declared to be free from earthquake hazard. This was 6 years before the 1933 Long Beach earthquake. Okay, so So that was in the 1920s. The real heyday for earthquake prediction research was later. It was basically in the 1970s. And it was tied very closely to a push for the first ever national program focused on earthquake hazard, what we call NEHRP, the National Earthquake Hazard Reduction Program, which was launched in 1977. So a number of things were going on in the 60s. The earth science community was pushing for a program to address and reduce earthquake hazard or earthquake risk. And a number of interesting things were going on in the world. There were some big earthquakes, including one that caused the first urban disaster in the US in a long time. There was an apparent success, in China, a prediction of the Haichang earthquake, and then in the Soviet Union, there was apparent success predicting earthquakes using what was called the VP-VS method. So VP is the velocity of P waves in the Earth, VS is the velocity of shear waves, and Soviet scientists were claiming that they could see changes in that quantity before earthquakes. Okay, so I just wanted to mention the Haichang prediction. It was an interesting story and one that I'm not going to have a chance to have time to go into. But it's a story, if you're interested, there was a scholarly article that was written about 10 years ago describing what had actually happened. There was a prediction made in advance of this earthquake, sort of. But at the same time, even through the heyday, there were some noted skeptics about earthquake prediction research, most notably and most vocally this guy, Charles Richter, who you may have heard of. He got his undergraduate degree in physics at Stanford. Looking back at this road to NEHRP, so there was always skepticism at the time, and in retrospect, looking back, there's sort of a cynical viewpoint that maybe earthquake prediction was held up as a carrot by people who were interested in launching the program. And it was a script that Hollywood could have loved. This was the height of the Cold War, and it was basically the Chinese and the Ruskies are ahead of us. We have to catch up. We need this program. Earthquake prediction is right around the corner. And that was actually kind of the viewpoint that I had in mind when I started to write the book, having gotten into the field just immediately after all of this played out. But talking with some of my colleagues who were young scientists through all of this, what I heard from them was different, that there really was genuine optimism that reliable earthquake prediction might be just around the corner, and it stemmed from a number of seminal papers that were published in the 60s and 70s that involved a number of things, induced earthquakes, dilatancy, if possible physical basis for earthquake prediction, just a series of papers, and I'll talk about them a little bit more in a second. But if you look at this list, you'll notice that 3 of these papers were published in Science, 1 in Geology, which is a prestigious earth science journal. So this was, the splashy science that was being done in the 70s was suggesting that maybe we're starting to understand the earthquake machine well enough that short-term prediction really was possible. One of the ideas that was first discussed was known as diffusion dilatancy, and it is basically, dilatancy is basically a process where materials are deformed and the volume increases, which leads to different material rock properties, which could explain why this VP-VS ratio would be different in the Earth before an earthquake happens. And I probably need to skip some of the gory details, but the basic idea was that increasing stress leads to physical changes in the Earth, which will lead to observable precursors, so things that happen in the Earth before large earthquakes occur. And one possible intriguing precursor was identified along the San Andreas fault near Palmdale, came to be known as the Palmdale Bulge. It was an observation of the Mojave Desert that had basically risen in this area in a short amount of time. And this was big news at the time. And so here's a quote taken from Time magazine. And one note for the students in this room is that it's hard to imagine how different things were back in the 70s. This wasn't only before the web, but it was before AOL. And so information came at people from a lot fewer directions. You had the network news, you had newspapers. Time and Newsweek were big time, big stuff. And so to have something like this in Time magazine was very influential. And yet, after all of that excitement and optimism and the launch of the NEHRP program, the hangover followed quite quickly. And it happened for a number of reasons. In 1976, one of the most deadly earthquakes of all time happened in China that was not predicted. Predicted earthquakes, for example, in Southern California failed to materialize. Unpredicted earthquakes struck in a number of places. And the Palmdale Bulge was basically flattened, shades of Bailey Willis all over again, led by David Jackson, then at UCLA. He basically showed that the observation itself was mostly measurement error. So by 1982, Clarence Allen, who was one of the preeminent earthquake geologists of the 20th century, wrote this, that basically just 5 years after NEHRP was launched, earthquake prediction is a more difficult problem than most of us thought. Okay, so I wanted to use the rest of my talk to sort of go through some ideas about earthquake prediction in a post-hangover era. And I'm going to look at 4 different possible approaches to earthquake prediction. One is based on this simple idea of time predictability, which going back to this figure and the idea that, well, maybe at least some faults do have earthquakes with a low enough coefficient of variation that you can make meaningful predictions with this kind of data. The problem with this kind of approach is basically shown here. If you look at the fine print, you see that the 2 sigma uncertainties on this 151 years are actually 72 years. So the average time between 2 earthquakes between 2 big earthquakes on the Hayward Fault might be 151 years, but the 2 sigma range is a low of 80 years up to 220. And in a geologic time scale, that's still a fairly narrow range, but in a human lifetime, that makes all the difference. Okay, there is some evidence that, and one of the complexities, one of the reasons that earthquakes might not be periodic is the possibility that large earthquakes cluster. It's an observation that we have generally some empirical evidence for, including on the San Andreas Fault and the central segment as described in this paper. And there's a lot of phenomena in nature where clustering arises. An analogy, you can turn to something familiar, which is traffic. So say you're sitting on the median strip and you're told that cars come by on average every 5 seconds, and you're asked to predict when the next car is going to come by. If you're sitting here and a car has just come by, you might say with confidence that the next one's going to be 4 seconds away, when in fact you're in the middle of a cluster and it's going to come quickly. Whereas if you're sitting here and it's been 6 seconds, you may say with confidence it's going to come any second. And in fact, the fact that it's been a long time since the last one means you're in the middle of a long interval and you may still have a long time to wait. Okay, so even if earthquakes aren't regular in time, earthquakes might be predictable if we could identify precursors, so something that happens in the earth before large earthquakes occur. A lot of precursors have been proposed. Some of them are non-seismic, and there's a range of things, radon gas, cloud formations, electromagnetic signals, either terrestrial or ionospheric. And then a couple things that have emerged more recently called non-harmonic tremor, slow slip events. These are interesting. I'm not really going to talk about them. But the point here is that people have been doing work like this for a very long time. Just over 10 years ago, I went to an international geophysical meeting where there was a day and a half of sessions that were largely touting intriguing results, looking at these various sorts of precursors. And what you have to ask is, where's the track record? You know, people have been making these sorts of predictions or suggesting that these sorts of things might be precursors, and yet nobody has established a successful long-term prediction of large earthquakes. Okay, then there's the possibility that you have seismic precursors, and this is where I get at least a little bit into complexity theory, so if you're still with me. You may have seen this figure, which has been called the tombstone diagram. So what it shows is basically earthquakes in the San Francisco Bay Area leading up to 1906, and then afterwards, and they're stretched out horizontally just so you can see them, and you see all these earthquakes, 1906, and then things get quiet. And so that leads to a sort of a more complicated theory of an earthquake cycle where you start to get a lot of regional activity before the big one, and then things get quiet. And going back about 20 years now, that was formalized as the theory of accelerating moment release. So moment, you can think of it as seismic energy. It really isn't, but it's sort of close. So if you look at a region and you sum up the moment in that area over time, you start to see this acceleration that people were pointing to as a hallmark of a critical, of a system that's approaching criticality. And some people were even identifying these small scale fluctuations and linking that back to complexity theory. There were some results that, going back 20 years ago, looked quite intriguing, and they were, I think, effectively debunked by a paper that there was years of debate, but then 2008, it was essentially debunked by this paper that considered whether or not these observations were real and predictive, or if they could be an artifact of data selection biases. So, okay, to see how data selection biases go, they're insidious in this field. And seismicity is always complicated. This is a map I grabbed off the web whenever. And so if an earthquake happened anywhere, what we're doing developing earthquake prediction theories is always, almost always retrospective. The earthquake happens, and then we define a circle and say, oh, look, seismicity is increasing. But we have a lot of latitude in how we define that circle. And so what this paper showed is that you have enough latitude, even if you think you're being rigorous, that you can find any signal you want in a seismicity catalog. One of the examples they showed was the 2004 Sumatra earthquake that was touted as a successful example of accelerating moment release before this big earthquake. But they showed by choosing a slightly different box, you could actually find decelerating moment release. So basically, you can find any signal you want in an earthquake catalog. So going back to this figure, what's wrong with this figure? Okay, I told you one of the answers. There's two answers. I told you one is that I just said this is the San Francisco Bay Area, and you all nodded, right? I didn't define what the box was. I didn't tell you latitude, longitude. You do see the time, and it turns out that how you define the box does matter. If you make it a little bit bigger, you bring in earthquakes here that make this look a lot less convincing. The other thing is not going to be obvious to an audience that aren't earth scientists, but it's something near and dear to my heart. Now, how do we know the heights of these tombstones? These are earthquakes that happened before seismometers were even invented. And the magnitudes come from documented effects of these earthquakes, the damage that they did and where they were felt. And it turns out, in my humble opinion, that all of these tombstones are too high by about half a magnitude unit. And that's a whole nother talk. But Okay, well, maybe we can't do short-term prediction. What about this idea of short or intermediate-term forecasts? So can we identify earthquakes that are ripe or for a large earthquake, or earthquakes that are overdue? And this is tempting to do. For example, along the San Andreas in California, you have the northern segment, which last went in 1906. We are here. The central segment last went in 1857, and then the southern segment way back around 1700. So that's been a long time. And it's tempting to say overdue. But if you look back and pull out quotes, starting with our friend Bailey Willis in 1925, saying, you know, the earthquake's overdue, it's going to happen any second. 1969, the then director of the USGS testifying before Congress, we are predicting another massive earthquake, certainly within the next 30 years. 1992, scientists were afraid that the Landers earthquake was a precursor to a big earthquake on the central San Andreas. And then less than 10 years ago, again, the latest earthquake on the central San Andreas looks to be overdue. So the problem is that our ability to look at faults and really say whether or not they're ripe for a large earthquake maybe isn't as good as we like to think it is. We've been saying the same fault was overdue for about 80 years now. Okay, will prediction ever be possible? That's hard to answer, and interestingly, a quote by, this quote is by Richter himself. But I wanted to end as a responsible earth scientist on a note that earthquakes are unpredictable, but they're certainly not unforeseeable, and arguably they're predictable in the sense that matters. We know where earthquakes generally happen. We know the long-term rates that they happen at. If you look at the Caribbean plate, which is a small-scale ring of fire, you have the plates moving past each other. We can measure that with GPS. This isn't string theory. We can watch the plates move. And in 2008, there was a study looking at GPS that was talking about the potential for magnitude 7 or greater earthquakes in Hispaniola. And that was less than 2 years before the 2010 Haiti earthquake. So this wasn't a prediction, but it illustrates that we can, in fact, forecast earthquakes. And so I'm ending on this slide for two reasons. This is a map that I think you're going to see in the next talk, so this partly sets up Morgan Page's talk, but it makes the point that in areas like California, we do know where earthquakes are expected and at what long-term rate. Arguably, the problem with earthquake prediction is not that we don't understand the science, it's that human beings don't live long enough. So with that, I will stop talking. Thank you.
Thank you.